Okay, let's get started. These will be the lectures for Physics 101, Conceptual Physics, using the textbook right here. I am Dr. Raymond Rogers, and this is my email address. So here's kind of where we're going to go today. I've already told you a little bit about me, and I've already gone through the syllabus, so I'm going to talk about how to do well in this class, a little bit about the problem solving and messing around with the units that we'll be talking about, and then just talking about what is science, so starting in on chapter 1. So let's just get started with just some basic expectations for this course. Attend lectures, or actually in this case it's going to be watch the lectures. I do expect you to actually watch the lectures, and of course to participate. If something doesn't make sense, certainly do ask. There's no such thing as a stupid questions. No one is ever going to think, oh wow, he knows absolutely nothing. They're going to think, oh wow, he or she really wants to learn. Second thing to keep in mind is actually do the work. The only way you learn to do anything is to do it. If you want to become a good basketball player, then you need to play basketball. If you want to do well on a physics exam, then the only way to do that is to take a look at some physics problems. And of course, try to have a good time as we work our way through the class. This slide right here kind of talks to exactly what I said on the previous slide about actually doing the work, and this has been around since well before I was born. It's called Dale's Cone of Learning, and it really kind of relates what people remember to what they actually did. And what he kind of said is if you go ahead and read the book, you're going to pick up about 10% of it. You're going to pick up about 20% of what you hear, 30% of what you see. So watching a video or viewing images, you're going to take away about 30% of it, and it's really not all that good. 50% of what they see and hear, so watching demonstrations. I'm having some videos of me dropping balls and stuff like that. So you're still going to take away 50% of it. As you start to do more hands-on activity, saying things and writing things, you remember even more. And last but not least is going to be 90% of what you do, and that's kind of the purpose for the labs, to actually get some hands-on, to think about what's going on, and to write it down. So all of it's really not designed to make your life a pain in the butt. It's designed to help you remember things. Now, of course, I know in your mind is big question here is how much math is going to be in this class. This is, of course, conceptual physics, but there is a teeny tiny little bit of math. So it is largely a very qualitative course, and conceptual physics doesn't mean that the ideas are trivial or even simple. We will be using things like simple graphs and very, very, very basic algebra and averages. You don't need one of those fancy scientific calculators that does like everything, but say you can get away with a simpler calculator. I'll give you a brief example of some of the worst algebra that you'll possibly see on the next slide, but just don't let any of the math psych you out when you see it. So here's my confidence test for you on how your algebra is feeling. So here we have the expression for the volume of a sphere, and it's simply going to be 4/3 pi r cubed. And confidence test is go ahead and pause it right now and try to solve for r. So now that you've gone ahead and given that a whirl, let's say, well, how do we go ahead and how do we solve this guy for r? Well, the very first thing we want to do is we want to divide this side by pi. We want to get r by itself, and if you do that to one side, you need to do that to the other side, and those guys are going to cancel out. We're going to do the same thing. We're going to multiply this side by 3 because we want to cancel all the 3's out. If I do that to this side, I have to do that to this side as well. And then we want it to essentially divide by 4 because we want to be able to cancel out those guys. If I divided this side by 4, I need to divide this side by 4. So I'm just going to go ahead and write this guy right here just for clarity. 3v over 4 pi is equal to r cubed. And now I want to get rid of that cubed, so I go ahead and I take a cubed root of this side. If I do it to this side, I have to do it to this side. And for, well, lack of a better word, this is going to make this go away. And we're left with the radius of a sphere is equal to the cube root of 3v over 4 pi. Now, if that was kind of scary for you, then you might need to brush up on your algebra a little bit, and I'll say that this is the worst possible math that we're going to do. We're not going to be doing sines or cosines or anything crazy like that. So let's dive right into chapter 1 and talk about kind of what is science. When we're talking about science, what we're really trying to talk about is how can we describe the natural world around us. Of course, it builds upon a body of knowledge. Newton said that he was only able to see as far as he is able to see because he stood on the shoulders of giants. It is definitely something that is ongoing. We're still learning things about the natural world every single day, and we've been doing it for a very, very, very long time. Science has been going on pretty much since before recorded history. People were trying to predict the weather and figure out where various crops grew and where the animals going and everything like that. So as we kind of think about what science is, maybe ask yourself which one of these kind of best describes science. And actually this is a trick question. It's actually going to be all of these. It's going to be a compendium of answers or a body of knowledge. It's going to be a set of rules that describe the natural world and how it behaves. We know that if we drop balls, they're going to fall down to the ground. That's kind of a rule. It is a methodology of figuring these things out, so we'll talk a little bit about the scientific method in a little bit. It's a little bit about exploration and curiosity, trying to ask some questions that need to be answered. And of course, if you ask some questions that need to be answered, then you need to do some experiments and make some observations. And just a teeny tiny little bit of boring guys in white coats with nerdy senses of humor. Again, this is something that we've been doing for a very, very, very long time. Now, as we go ahead and ask questions about the natural world that is around us and try to make some observations and come up with answers, we definitely need to make scientific measurements. And essentially, a very brilliant scientist by the name of Louis Kelvin said, measurements are the hallmark of good science. Now, what scientific measurements allow us to do is they allow us to relate things that you know to things that you want to know. For example, if you had a sheet of paper, just like this one right here, and you cut a hole in it and you were able to measure that hole right there, you were to hold it off the ground, and then you were to say, measure the image that the sun makes on the ground. So go ahead and measure that guy right there. Then it turns out that using these two things that you know that and you know this, you can actually figure out the diameter of the sun if you know how far away it is. So what scientific measurements allow us to do is going to be relating things that you know to things that you want to know. Now, just to kind of drive home the point that we've been making scientific measurements for a very long time, in Egypt, around 253 BC, this fellow right here took the first stab at the diameter and circumference of the Earth, and what he knew was that on June 22nd, that's going to be the longest day of the year, at solar noon, that if you had a well in this city right here, then the sun does not cast a shadow whatsoever. And what he did was he took a really long pillar right over here. He went to the city of Alexandria and he measured the height of the shadow, and then what he did was he mumbled something about similar triangles, and that allowed him to figure out that angle right here was the same as this angle right here. He was able to figure out the distance between these two cities, and then he was able to say, okay, well, if I know the distance between the two cities, I could say c is equal to 2 pi r, where this is the circumference of the Earth. That allowed him to figure out the radius of the Earth. Again, we're relating things that we know or things that we can measure the shadow, to things that we don't know, the radius of the Earth. And this kind of scientific inquiry and measurements continued still in the early 240 BC time frame, with kind of the first estimate of the distance and the size to the moon made by this fellow right here. And believe it or not, he was actually accurate to within 5% of the value that's accepted today. And what he did was he took a measurement of the moon's shadow during a solar eclipse, and he was able to figure out that the Earth's shadow was about 2.5 times wider than the moon during a lunar eclipse. And so he figured out that the Earth should be about 3.5 times the diameter of the moon, and we knew the diameter of the Earth from the previous measurement, so he was able to kind of gin up the distance and size of the moon. Now, one common theme that you saw on the past several slides was the use of similar triangles and the use of mathematics. It turns out that math really is the language of science, and it's been occurring for a very long time. Very often we express these ideas of science in terms of mathematics. Now, keep in mind this is conceptual physics, and I will try to keep the equations to a bare minimum, and they'll be the simplest possible ones. But when we think about the equations that we'll be talking about, really they're kind of a guide to thinking about things.